Okay, so this is really complicated stuff, and to really understand aqueous chemistry, which we're not going into in a ton of detail in this quarter, but you would really need to know about chemical equilibria, activation energies, free energies, and solubility constants. And we just can't go into all of that in this program. So even though we don't have time to go over all these things, I will try to do a good review of redox because oxidation reduction reactions are so important in terms of biogeochemistry. So oxidation reduction potential is the relative availability of electrons for chemical reactions in a solution. It's also called the redox potential. It's all about electrons. Okay, so I put up a picture of an electron if you just need, or an atom, so you can see the electrons, the protons and neutrons in the middle, and the electrons are buzzing all around in these orbitals. Now, the redox potential is kind of an overall measure of how tightly the electrons are held and how available they are. So in a chemical reaction, most chemical reactions, a lot of chemical reactions, one molecule gains electrons and another molecule loses them. Now, oxygen has a really high affinity for electrons, and this is why we use the word oxidation. It tends to oxidize other compounds. So oxidation stands for, oxidation reduction reactions. You can use this mnemonic, oil rig. So oxidation is losing electrons. Reduction is gaining electrons. So the redox potential determines which chemical reactions will occur without an input of energy and what products will be favored. And so it's important for understanding natural systems because there's not a lot of extra energy to drive reactions out there other than light energy. Oxidation reactions will be inhibited. They are thermodynamically unfavorable if the environment is reducing, if it's electron-rich environment. Okay, and the opposite is true. Oxidation reduction potential, or ORP, reflects the relative abundance of electrons that are available for chemical and biochemical reactions in the environment. And you can measure ORP using an electrochemical probe. It compares the capacity of the environment for donating reduction or accepting oxidation electrons relative to that of a standard platinum electrode for hydrogen. So there's some really great videos out there on oxidation reduction, and I'm not a chemist, so I don't really want to be the one teaching you this stuff, but I'll just give you some of the rules about oxidation numbers. So free elements are 0, they have 0. Ions have as many basically electrons as the charge. So, and then oxygen is always -2. Peroxides are -1. Hydrogen is +1 when it's connected with nonmetals, or -1 when it's connected with metals. And so in neutral compounds with no charge, the sum is 0. Or if they have a charge, like an ion, then the sum will be whatever the charge is. Okay. So for example, hydrogen is a +1 in this case, and oxygen is always -2. So since there's 2 hydrogens there, we have +2 -2, and so the charge is 0. And that makes sense because water is not a charged compound. In Na2SO3, Na has a +1 charge, and there's 2 pluses there. S has a +4 charge, and O has a -2. There's 3 O's, so that makes -6 and +6. So there's overall neutral charge, neutral charge. For sulfate, there's 6 for S, and you can see sometimes for S here, it's a different value. And so you always start with what you know, like oxygen is always -2. So because oxygen is -2 and there's 4 oxygens, then, and we know that sulfate has an overall -2 charge. That'd be -8 with a -2. We know that the sulfur has to have a +6 for its oxidation number. Okay, so oxidation numbers are not charges. They're not always charges. Sometimes it's the charge, sometimes it's not. It is definitely a little bit complicated. So we'll have some practice. I have a worksheet that shows you some practice examples. So redox reaction rules, free elements have an oxidation number of 0. So hydrogen gas, magnesium, sulfur, all 0. Ions tend to match their charge. So NaCl, +1, -1. A positive potassium would have a +1. Magnesium chloride, +2, -1. Okay. Oxygen is always -2. Unless it's in a peroxide, then it's -1. Hydrogen is always +1 with nonmetals, -1 with metals. This is kind of redundant, actually. Very redundant. Sorry about that. Good review. Okay. Some elements change their oxidation numbers widely, like I showed you with sulfur there. Okay. So here's an example. We're going to follow the electron. So what happens to the electrons as magnesium solid is mixed with hydrochloric acid and turns into magnesium chloride and hydrogen gas? Here we would look at the oxidation numbers. So magnesium has a 0. Hydrogen and chloride, okay, +1, -1. Moving to now magnesium is an ion, and it's forming an ionic bond with the chlorides. And there's 2 chlorides, they're -1, magnesium is +2. And then we have hydrogen gas. So what happened to these things? First of all, magnesium went from 0 to +2, and hydrogen went from +1 to 0. So magnesium lost 2 electrons because it went from 0 to +2. So it lost 2 electrons, and now it's positive, has a positive charge. Hydrogen gained 2 electrons, and so it was reduced. And so it went from a +1 charge to a 0 charge, and there were 2 of them. Okay, so in this case, magnesium was oxidized, even though it's not joined up with oxygen, okay, and hydrogen was reduced. Okay, here's another example, the Haber-Basch process. Ammonia, we take nitrogen gas, okay, so this is what we do to try to create fertilizer from nitrogen gas. Take nitrogen gas and hydrogen gas. Nitrogen gas is a 0 charge, and it is reduced because it's gained 3 electrons when it's formed in with hydrogen to make ammonia. And the hydrogen goes from 0, 3 hydrogen, or yeah, actually six of them, right? Because there's 3 hydrogen gases going from 0 charge to +1. So it has lost electrons. It's lost 6 electrons. Okay. So this is important. Redox is important in nutrient cycling because oxidation reactions yield energy under oxidizing conditions. Reduction reactions yield energy under reducing conditions. And so if we have an oxidizing environment and we want to take ammonium and turn it into nitrate, we can yield energy. And there's organisms that do this work and they make energy for themselves. And that's going with potential energy. In a reducing environment, an organism might take nitrate and convert it into ammonium, and that will yield energy. And that will also be going with potential energy. So the top 2 yield energy. Now, the bottom 2, if you're in an oxidizing environment and you want to take nitrate and convert it into ammonium, that's going to require energy. And the same is true in a reducing environment to take ammonium and turn it into nitrate. And so it's important to understand these redox reactions because you know what's going to be energy efficient and what's going to be really challenging. So the activation energy is the energy required to move from one form to another, or one state, to another. Oops, sorry, to move from a state of low to from high to low potential energy. And reverse reactions require energy inputs. Okay, so these, what are shown on the right, are called Gibbs free energy diagrams. So a lot of microbes do this important work of redox chemistry, and they do it because they make energy, and that's how they make their living. So a lot of microbe-mediated chemical reactions involve redox reactions. And so these arrows, so the top are showing reduction reactions and the bottom are showing oxidation reactions. And the difference between the tail and the head of the arrow tells you how much energy is yielded through that reaction. And it also shows you like where in the redox potential kind of environment, where will this reaction take place, basically without the input of additional energy. Oops. So some important things on here, of course, we're interested in things like denitrification. We're interested in nitrate reduction. We're interested in sulfate reduction and methane fermentation. We're interested in nitrogen fixation, so N2 to NH4. We're also interested in iron oxidation. So that's just rusting. We're interested in rust because it damages metal objects, but we're also interested in iron oxidation because a lot of bacteria oxidize iron as part of their job. We're also interested in the conversion of nitrogen gas into nitrate and ammonium into nitrate. And so all of these reactions are part of key critical pieces of biogeochemical cycles that we'll talk about in the future. Okay, so chemical compounds have potential energy when they have a redox that's different from the average redox of the rest of the compounds in the solution. So a low redox compound in a high redox environment has a lot of potential energy, and a high redox compound in a low redox environment has a lot of potential energy. A transformation will yield energy if the redox potential of the solution is less than the head of the arrow for reductions or greater than the head of the arrow for oxidations. So this tells you when certain things will yield energy. So some redox reactions require energy, and that's called the activation energy. And a reaction will not occur if the activation energy is too high. One of the primary determinants of whether redox reactions takes place is the presence of oxygen gas. So some reactions need to be protected from oxygen gas, and some reactions require oxygen gas. And organisms can drive reactions against potential energy. So given the input of other energy like light in photosynthesis, organisms can push a chemical reaction that goes against what should happen due to the redox of the environment. And so photosynthesis is a great example of this. So if you've ever been next to a stream and you've seen this weird like gush or puddle of really orange looking gooey stuff and you've gone, gross, that's pollution, you're probably wrong. It's probably not pollution. What it is likely is iron oxidizing bacteria. And so often groundwater is really high in iron. And so when it comes out of the ground, when it seeps sometimes on the edge of a stream, you'll get this nice gush of groundwater coming in. That iron, when it hits the atmosphere, it rusts. And it rusts because there are iron oxidizing bacteria present that help that reaction along. Okay. So these bacteria are using energy from that reaction to grow. And sometimes it'll be accompanied by like what looks like kind of oily, like an oil slick on the surface. It's not actually probably oil pollution, but just the lipids involved in the growth and breakdown of these bacteria. So one way you can tell is if you touch the oil and it kind of cracks apart, then it's biological lipids. If you touch it and it just spreads apart and comes back together, then it's probably petroleum. So if the oily sheen stays separated when you disturb it, then it's probably just lipids associated with these bacteria. And then just real briefly, I just want to kind of come back to these tables. I've shown you these before, but these show you electron donors and electron acceptors. This is the key currency of redox reactions. Okay, so it's showing you, this table is actually showing you what compounds are donating electrons and what compounds are accepting electrons. Okay, and so maybe this table, I would spend a little time just kind of looking at it and thinking about it from a redox perspective. Okay. moving on.